things I want you guys to see as we go through today's session, and then as we go into next week as well. Um, the the exam now is 2 weeks, is less than 2 weeks away, so we're now 11 days from the AP Stats exam. We're sitting here in Unit 2 and we're reviewing, but I also want to show you something else that we are going to try to do next week. We'll try to build in a little bit of time next week at the very end to do that, maybe the day before the exam, I think would be a good idea. But I'm going to show it to you and kind of give you kind of an update. But basically, there's never been an exam like this before. So what Stats Medic and some other AP Stats teachers have done, and let me just read through this to you, but basically in years past, we've always had students take a full-length practice exam, and we actually had one scheduled at Lincolnton for April 25th, where we were going to do one this year. And we would go on a Saturday, and you would get a test. You would get it would help your test grade and all that. But what they've done is they have created a practice exam for this year. So this year you're going to have a 25-minute free response question number 1 and a 15-minute free response question number 2, and each question goes over multiple content areas, and it will cover content from each of the units, from units 1 through 7. And questions are going to be written so that students can complete them without the use of a statistical calculator. You may use a calculator, but you may not need to, is what they're saying, just in case. And there's no investigative task. That means there's no really long problem at the end that there typically was in previous AP Stats exams. So what they have done basically is presented a practice exam. So there is a practice exam, and we can administer this exam to you via Zoom, so we can talk about it on here, and you can practice taking that 45-minute exam, and then we can go over the answers. So I think that's going to be a really, really good idea as far as if you want to be prepared, because it's really hard to be prepared for an exam that's brand new. But some of the people that have worked on that exam and have thought through it are trying to help create this for you as a sample, kind of like practice for this is what you need to do. So what I'd like for us to do is to kind of put that in our plans for May 21st. So on May 21st, we may not talk as much about significance tests, since we've just done those, and those were like the most updated thing possible. I may just leave you with a video to watch maybe the night before on that. But with the exam being on the 22nd, I can't think of a better way to practice than to go through and do a full practice exam the day before. And it only being 45 minutes, that's not going to take a lot of your time. You can do it right during this little class period. We can go over the answers right here during this little 10 to 11 block, and that'll be a good practice. And then if for some reason you aren't able to be there during that block, we can always record that and set it up for you as well. Okay, so let's go today. If you look on so if we go to the Stats Medic, we're in the review course here, and in the I need to log into it. But in the review course, we've had a couple things that we've gone through. Have been we've gone through all of Unit 1, which was one variable statistics. So in Unit 1, we took everything that we were doing and we used one variable statistics. So that meant like stem plots, that meant like box plots, that meant histograms, bar graphs, anything that can be done with just one variable. And then in Unit 2, we're talking about two variable data. So we watched a video on how you describe a relationship. So that's the shape, outlier, center, spread. We talked about all of that. How would I describe the relationship between two variables, or between these two things. Then we talked about making predictions. So the least squares regression line helps you to make the prediction. The residuals tell you how far away your actual value was from the predicted value. And then we worked on a free response question that kind of incorporated a lot of that together. So today, we want to go through these 10 multiple choice questions together. If you don't have the printout, they're right here. So if you'll go into Unit 2 on Stats Medic and click the practice multiple choice, you'll be able to see them. And I'm going to go over them on my own paper. So we're going to go through these 10 multiple choice questions. We'll then jump to the practice free response question and then go over it. And we'll be done with Unit 2. So after today, we'll be done with 2 units. Just a quick preview. What we're looking for Tuesday and Wednesday is to go through all of Unit 3, Thursday and Friday to go through all of Unit 4, and that'll cut us at May 15th. Then next week, we're looking for Monday and Tuesday to go through Unit 5. On Wednesday, we're looking to maybe look at confidence intervals and significance tests together just kind of quickly. And then on Thursday, taking that practice exam. And then Friday will be your actual AP Stats exam online. Okay? So that's the setup. That's what we're looking to go through during these sessions. If you missed any of the other videos, remember they're posted on YouTube, and they're also posted on your class page. But this is the fifth installment out of the 13. So today's the 5th one. All right. So let me take you to the Unit 2 multiple choice. So let's go through these together. If you want to help me answer these, let me know by either saying something in the chat, or you can unmute yourself as you go through the problem as you try to answer it. So number 1, which of the following relationships between two variables could be described using correlation R? So which of the following relationships between two variables could be described using the correlation, which is R? Now, when we talk about using R can only be used to describe two quantitative variables. Okay? So we need two variables that have numbers. So which of these scenarios, A, B, C, D, or E, gives us two variables that can both be described quantitatively? And two variables that will both be described with numbers. Numbers. So C says the high temperature of the day. That's going to be a number, right? And the number of zoo visitors that day. That's going to be a number. So both of those are described with numbers in C. Let's look at each of them real quick. In A, the gender of the student is categorical. In B, the position of a football player is categorical. In D, the type of beverage is categorical. And in E, the brand of cell phone would be categorical. So to use correlation R, you basically have to be able to create a scatter plot. And to create a scatter plot, you've got to have two quantitative variables, two things that you can describe with numbers. That's how we create our scatter plot. So that is question number 1. All right, 2. Let's look at 2. A scatter plot shows a strong positive linear relationship between the number of rebounds a basketball team averages and the number of wins that team records in a season. Which conclusion is most appropriate? Number 2, anybody got an idea? Give me your thoughts here. So again, the scatter plot shows a strong positive linear relationship between the number of rebounds a basketball team averages and the number of wins the team records in a season. Which conclusion is most appropriate? Okay, so I'm going to go through. This is a tricky one for you. The answer to this is actually E. Now I'm going to go through why. In this, so just because something has a high correlation does not mean that one thing causes the other to happen. It just may mean that they have a relationship with each other. So, like, for instance, as ice cream sales go up, the number of flu cases go down. We talked about that. That has a good linear relationship with each other because it's true. In the but really the what's causing the ice cream sales to go up is the time of year, and what's causing the flu to go down is the time of year, right? So this is kind of the same thing. Rebounds obviously they have a positive relationship with the number of wins, and the better your team rebounds, then more than likely the better they're going to win, and maybe the better they do at other things. But rebounds and wins are positively correlated, but we cannot conclude that getting more rebounds causes more wins. So the key word here was causes. So cause and effect can only be, you can only show cause and effect through a well-designed experiment. So this is not an experiment. This is just an observational study, just looking at them. And so in all of these, you see the word causes. The number of rebounds causes its chances of winning to increase. It's safe to conclude that getting more rebounds causes more wins. It's safe to conclude that getting more wins causes more rebounds. It's safe to conclude that getting more rebounds causes more wins. So in all of those, it says that it causes the other to happen. We don't know that getting more rebounds actually causes them to get more wins, or if it's something else, right? It could be the fact that they shoot better or that they play better defense. So rebounds and wins, we know have a positive correlation. We know there's a relationship there, but we cannot conclude that getting more rebounds actually causes more wins to happen on average. Okay, so let's go to number 3. Number 3 says 2 variables, X and Y, have a correlation of 0.75. Okay, they have if X has a mean of 25 and a standard deviation of 3, and Y has a mean of 12 and a standard deviation of 6, which of the following is the least squares regression line? All right, so to find the least squares regression line, here's what you would have to do. So it looks like this. Here's our formulas. It's giving you a bunch of stuff. This is in your formula sheet. So Y hat equals B0 plus B1 of X. Okay, it looks like this. So the first thing we can find is called B1. All right, so in B1, the formula for it is R times SY over SX. Then the formula for B0, make sure I've got that for you there. Formula for B0 or B sub naught is the mean, sorry. The formula for B sub naught is the mean of Y minus B1 times the mean of X. So based on the formula for B0, you have to have B1 in it, so you have to do B1 first. So R is the correlation. So it tells us the correlation is 0.75. So that's our R, 0.75, times, we need the standard deviation of Y. So Y has a mean of 12 and a standard deviation of 6. So the standard deviation of Y is 6, and then we need a standard deviation of X. X has a mean of 25 and a standard deviation of 3. So 0.75 times 6 over 3. So that would be 0.75 times 2. So that gives us 1.5. So we found B1. That's our slope basically. We found it. And you see that in answer choice A, and you see that in answer choice B. So now we just have to find the y-intercept. So the y-intercept is going to be the mean of y. We found the mean of y is 12 minus 1.5 times the mean of x. The mean of x is 25. Okay? So that's 12 minus 1.5 times 25 is 37.5, which is going to leave us with negative 25.5. And that is going to be our y-intercept. So at this point, sorry, I moved the paper just a little bit. So at this point, we have found the slope and we found the y-intercept. So we're able to write the equation y hat equals negative 25.5 plus 1.5 times x. And those formulas are given to you on the formula sheet if you had to use that, okay? So those would be given to you on the formula sheet. This would actually be something that you would not have to do, you would not necessarily need a calculator for, right? Because they're very easy calculations, like 6 over 3 is 2, 0.75 times 2 is 1.5, and then to try to make those calculations, you wouldn't necessarily need the calculator. So that's number 3. Let's move forward to question number 4. It says data are collected on the amount of fat in grams and calories in the French fry orders at 9 fast food restaurants. The least squares regression line for the data is y hat equals 274.34 plus 9.55x, where y hat is the predicted number of calories and x is the grams of fat. Which of the following is the correct interpretation of the slope of the least squares regression line? So the slope is 9.55. So what is the correct interpretation of that slope? Anybody give me that one? The correct interpretation of slope. I like that. D, Will, so that's right. D, for every 1 increase in gram of fat, the predicted calories increase by 9.55. So remember, for every 1 increase in X, that would be fat, the predicted Y, remember it has to be predicted, increase by 9.55. And that's what our slope is for anything. For every 1 increase in X, this is how much Y is predicted to increase by. Now notice in C, every increase of 1 gram of fat causes an increase of 9.55 calories. So that's a definitive statement. And in this case, we're only talking about the prediction equation. So we have to use the word, when you're doing slope, we have to say it increases by that much on average when we're interpreting slope, or we predict, or we think it will, or we estimate that it will increase by that much. We can't say for sure that it will increase by that much every time, because this is just a prediction. So good job. Number 5, the scatter plot below shows data for the 9 French fry orders from the previous problem with the least squares regression line displayed. Which of the following is the best estimate of the residual for the point indicated by the arrow? So here is this point, okay? What do you think its actual calories were right there? Any idea what you think the actual, let's see if we can, so we can make a line, right? So what do you think the actual, where do you think this point is? What's the X and the Y? What's the actual, so what's the, how many grams of fat and how many calories do you think? Let's do that first. What's 37 and, yeah, I would say it could be 560. I think it's a little bit above 560. It's definitely 37 on the x-axis. I would say 570 on the y-axis. But if you said 560, I don't think you're going to be wrong here, okay, because you'll see in just a minute how this will work. Now, so the 570 is the actual y, right? The predicted y we would get from the equation from the previous problem, right? So 274.34 plus 9.55x. Now, in this case, we're saying x is 37. So 274.34 plus 9.55 times 37. We want to see what that is. That will be our predicted y. So we get our calculator and we say 274.34 plus 9.55 parentheses 37. We get 627.69. 627.69. All right, that is our predicted y, okay? So let's go back. So there's our predicted, there's our actual. Remember, a residual, so I'm going to scroll down. A residual is the actual y, remember AP, right? Actual y minus the predicted y. So our actual y here was 570 minus our predicted y here was 627.69. So we get a negative 57.69. Now, when we look at our answer choices, we can see clearly it's got to be C, negative 60, because it's saying which is the best estimate, right? So it's the closest one. Now, you also see 60s on there. So if you would have done predicted minus actual, if you would have done the wrong way, if you would have flipped your residual, then you would have gotten an answer choice, but it would be the wrong answer. You see 630s on there because that's your predicted y. You see 570s on there because that's your observed y. So you've got to be careful with all the number choices that they're giving you on that one. Okay, that's number 5. All right, we're halfway through the multiple choice here. Let's move to number 6. The scatter plot below shows data for the 9 French fry orders from the previous problem. A 10th fast food chain has been added as indicated by the arrow. So this is a 10th fast food chain. So there were 9, and we've added a 10th one here. What happens? How does this number here affect the slope and the correlation? So how would that point affect the slope, and how would that point affect the correlation? What do you think? Well, first of all, correlation is decided based on how close the point is to the line. Is this point very close to the line that we already have? Is this point very close to the line? Yeah, it is. So it should increase our correlation. So we don't have to worry about, so anyone that says the correlation decreases, we can get rid of that. So it's going to increase our correlation because the point is very close to the line. But is the point above or below the line? It's the point above or below. So it's below. So anytime you add a new point, it will always pull the line towards the point. So if the point's below the line, it's going to pull your line down a little bit. If the point was above the line, it would pull your line up a little bit, right? So this is going to pull the line down just a little bit, which means the slope decreases as the correlation increases, and that is going to give us A. So because the point is below the current line, then we're going to say that the slope decreases, but the correlation increases because the points are very, very close to the line. Anybody have a question there? All right. I'm going to move to number 7. Number 7 says battery life has a strong negative linear relationship with temperature. If the least squares regression line using X is temperature, explains 90% of the variation in battery life, what must be the correlation? So what is this right here? The line explains 90% of the variation in battery life. What is that? What is that? Yeah, StatsMedic does say the answer is B for number 6. I tend to disagree there, because if you bring in a point below the line, it is anytime if you put points down here, anywhere below the line you put points, the line is going to go with it. And anytime you put points up here, the line is going to go with it. So I disagreed with their answer choice there. I can't see how the slope would increase when you put a point down below the line. It doesn't make sense, in my opinion. Okay, so what is this? Temperature explains 90% of the variation in battery life. Where have you seen that? What type of, anybody know what that is? That's not our R. What is it? It's our what? Not the R value. It's not the correlation, but it is the what? Yep, it's the R squared. So anytime R squared is the percent of variation in Y that can be explained by the line, okay? So it's the percent of variation in Y that can be explained by the line. So our R squared in this case is 90%, so 0.90. So how would we get our R? Well, we would just take the square root of 0.90. That's how you get from R squared to R. So we're going to take the square root of 0.90. And I get 0.948, which is going to give me 0.95. Now, we have to be careful here. So I get 0.95. However, if you notice, it says battery life has a strong negative linear relationship. So our correlation must be a negative 0.95. And that is C. That's number 7. Okay. So let's move to this number 8. As we go through these, we're doing pretty good so far. Number 8 shows us a table. This is good to see. They want you to be able to see a computer printout. So this is from like Minitab, the computer printout, and we need to get the equation of least squares regression line. So basically, the number of hours spent watching television and the power consumption during the day are recorded for every household, and we assume that like the more television you watch, the more power you consume. And this is a table. So you see the word constant here. Constant is always your y-intercept, right? So if you want to write that, that's fine. And then hours of television, that is always your x, or what's called your slope, right? So the constant coefficient, that is the number by itself. That's the y-intercept. The hours of television would be our slope. So if our equation is y hat equals a plus bx, then The y-intercept is the constant. It's 19.31. And the slope, the hours of television, is the slope. It's 0.891x. So 19.31 plus 0.891x, that is A for number 8. Anybody have a question there? All right, we'll move down. That's an easy one as long as you know what each thing stands for here. And that's the important part. You see the R squared is 0.30. So if they ask you for the R, the correlation, you could get that from here. You would always want to use the R squared, not the R squared adjusted. Okay, number 9. A random sample of households is taken. For each household, the number of hours spent watching television and power consumption. So we got the same problem. The table below shows the computer output from linear regression analysis. Here is R squared. It's 30%. This is our R squared. It says, which of the following is the correct interpretation of that? So when we're interpreting R squared, what are we looking for? We're looking for, in our interpretation, we're looking for a percent, and we're looking for variability, and it should be in Y. So it's, again, the interpretation of R squared is the percent of variability in Y that is explained by the line, okay? So 30% of the variability in power consumption. And we know power consumption is our Y because hours of television is our X. So the number of hours of television should explain 30% of the variability in power consumption. That's not a lot, right? So if the number of hours of television only explains 30% of the power consumption, then what that means is that if the number of hours of television will only explain 30% of the hours of the variability in power consumption, that means 70% of the variability in power consumption is actually explained by something else. So we want our R squared to be really high so that to show that this variable is explaining this other variable. But if our R squared's not, then what it means is something else explains it. So that means we can't just use our prediction as well. We won't have a good prediction because there are other things that explain the changes other than our X value. Okay, so that was number 9. We'll move to question number 10. This is our last question here. So using the least squares regression line, what is the residual for the data point at 2819? So 19 obviously is our observed Y, it's our actual Y, and 28, we would plug that in to our equation. We would plug 28 in for X, and we would be able to get our predicted Y. So if you go to your calculator and plug 28 in for X, you're going to get negative, so you do 5.5 plus 1.5 times 28, you get 16.5. So that is our predicted Y. So we're going to write, again, remember residual equals actual Y minus predicted Y. And so in this case, our actual Y is given to us as 19, and our predicted Y is 16.5, and so we get 2.5 as our residual. Now, again, notice that what you're going to see, notice that you see negative 2.5 as an option too. So they are hoping that you're going to mess those up or get those backwards. So you really want to be careful with that. I would say as part of a free response question on the exam, this would be a great part of like a 5-part question, would be to just ask what's the residual, and you have to calculate it, right? Because you don't really need the calculator. You could use it, but you have your actual y, you have your equation, you plug in x to get your predicted y, you do actual minus predicted, and you have your answer. So finding a residual is an important part in Unit 2 of 2 variable data. So it's definitely something that they can ask on the exam. Another thing they can ask on the exam is your interpretation. So you need to look at your interpretations of slope. You need to look at how you describe the data and things like that. So that takes us through the multiple choice. And so let's go now to the Unit 2 practice free response question. So if we go to that question, there's an A, B, and a C here on the Unit 2 practice free response. So if you'll turn your page or turn on the StatsMedic site to that next question, there's a PDF you can download if you don't already have the paper. I do already have the paper for you as well. So let's read through this, and then let's talk about what we think is best here. So the computer output below gives results from the linear regression analysis for predicting the pounds of fuel consumed based on the distance traveled in miles. So the distance traveled in miles is our x, and the pounds of fuel consumed is what we're predicting, so it's our y, right? For passenger aircraft, data used for this analysis were obtained from 10 randomly selected flights. So basically, we know how far the flights went, and we want to see if the distance that the flights traveled will help us predict how many pounds of fuel the airplane actually consumed. A, what is the equation of the least squares regression line that describes the relationship between the distance traveled in miles and the pounds of fuels consumed? Define any variables used in this equation. So first of all, x is going to be defined as the distance in miles, and y is going to be defined as the pounds of fuel consumed. And we've already talked about how we get the constant coefficient is our y-intercept, and then this is our x, and you have your slope there. So y hat equals a plus bx. So y hat equals the y-intercept, so negative 4,702.64, plus our b, which is the slope, 21.282x. So we have in A, there were 2 parts to this. Did you define your variables correctly? So do you have x as the distance in miles? Do you have y as the pounds of fuel consumed? And then do you have the correct linear regression equation? And to get you need the correct equation here in A to be able to get B as well. Or, well, you don't need it to be able to get B, but if it was asking you about a residual, a specific residual, you would need it. In that case, if you calculated the wrong equation and then it asked you about a specific residual, but you did the second part right, you can still get credit for the second part even though you had the wrong equation. Okay, so let's go to B. Below is a residual plot for the 10 flights. Is it appropriate to use the linear regression to make this? So do you see any obvious pattern in this data? In this residual plot, is there any obvious pattern? I don't see it, so we say no. We say, is it appropriate to use a linear regression equation to make predictions? We say yes, because there is no obvious pattern. In the residual plot. And for an obvious pattern, we would look for, like, Is there like a straight line going through? Is there a curve, like you can make a U exactly through it, but there's not, because we have above, below, below, above, below, above. So it seems like they're just some are above, some are below, some are above, some are below. And honestly, there's about 5 below and 5 above. So, I mean, that's what we expect to see in a residual plot. We expect to see some that were below what was predicted, some that were above what was predicted, and they're kind of scattered. And that's good. That's what you want to see to show that there's a appropriate linear equation. So we go to C. C is our interpreting part. It says interpret the y-intercept in the context of the problem. So the y-intercept is negative 4,702.64. And so it would be, so let's think about what that would be. If x is 0, this is y. So if the plane traveled 0 miles, it would be predicted to use negative 4,702.64 pounds of fuel. Now, is that meaningful? Is that possible? Is that even like, what's the issue here? You can't use negative pounds of fuel, right? So basically, this equation is taken from airplanes. And airplanes, if you're flying a plane, typically you're going hundreds, if not thousands of miles, right, away. So we are able to predict when we're going long distances. This would be extrapolation, right, because we're far away from what's predicted. You're not going to have a plane fly 0 miles, and you're also not going to be able to use negative pounds of fuel. So we would say this value is not statistically meaningful. First of all, you would say it's not statistically meaningful. Because a plane would not have a flight covering 0 miles. Okay. You could also say, you don't need to, but you could also say that you would not have there's no way to have negative pounds of fuel used. But the key is, when we try to interpret the y-intercept, that means when x is 0, what is y? Well, in this case, x being 0 would mean that the distance traveled on this flight was 0 miles. Well, that's impossible. You're not going to, anytime a plane takes off, it's traveled something. So this value is not statistically meaningful because a plane would not have a flight covering 0 miles. That's the key. If you want to tell what the y-intercept is, you want to interpret it in the context of the problem. So if the plane traveled 0 miles, so if x was 0, it would be predicted to use negative 4,702.64 pounds of fuel. And then we want to say, is this statistically meaningful? That kind of just means, does it make sense statistically? And this value is not statistically meaningful because a plane would not have a flight covering 0 miles. And that's really the key in this one. And you could say that that was extrapolation. So we're trying to predict the pounds of fuel for an X value that is far away from anything in our data. We know our data from our flights is probably hundreds and thousands of miles. Even though we don't have that data, we know that planes fly long distances. So that should be the reason why there. Okay. Does anybody have a question on that Unit 2 free response question here, this A, B, and C? It's a good regression equation. We really didn't need our calculator like at all for that one. So that's something that you could see parts of this asked on the exam for Unit 2. That's why it's here as a practice free response. Any questions or comments about that or anything in Unit 2? So at this time, is there anything in Unit 2 that we need to recap or I need to explain before we move forward into Unit 3 tomorrow? Okay, if not, here's what I'm going to do. I'm going to change my sharing. I'm going to share with you the screen. If you look at your solution, we just talked about it. There was our first equation. Y is the predicted fuel consumed. X is the distance in miles. Linear regression model is appropriate because there's no obvious pattern in the residual plot. The y-intercept means that the plane traveling 0 miles will be predicted to consume negative 4,702.64 pounds of fuel. Since the plane would not have a flight covering 0 miles, this number is not statistically meaningful. So that's the perfect response that they had there. If you go back now to the course, we should have completed Unit 2. So we've done everything for 2 variable data. So now, tomorrow, where we're going to head is into Unit 3, which is sampling and experiments. So in Unit 3, we're going to look at different sampling methods. What are all the different sampling methods, and what are the issues that arise that might make them biased or not a good method? Then we're going to look at how do you design an experiment and different ways of designing an experiment. Remember how you need it to be randomized and how you have to go through all these different things. So how do you design an experiment? And then we'll take a look at a free response question that was on the 2016 exam. So that'll be our goal tomorrow, to go through the sampling methods and some issues that arise, to go through how you design an experiment, and then take one question that's been used on a previous exam and try to go through it specifically. So thanks for being here, either live or for watching the recording. And I hope you continue to work through this. This is part 5. Again, we want to go through all the units and get through a little bit of all 7 units. And then on the last day, we also want to take a practice 45-minute exam to prepare us for May 22nd. If you continue to watch these and you continue to follow along and work through this, you're going to be more than prepared. You're going to be extremely prepared and ready to do extremely well on this exam. So thanks for being here, and we're going to end the meeting now. And I appreciate all your work, and we'll see you tomorrow. If you have any questions, let me know.